And Jimmy, you just start when you feel comfortable. Okay.
All right, welcome everybody to this week's Green Bank Observatory Community Zoom. I'm Jim Jackson. Happy New Year, everybody. I hope everyone had a restful and happy holiday where now the tissues are restored and the brains are recharged and we're ready to sally forth into a bold new year. Very happy to resume operations here at Green Bank, or resume our community Zooms. Operations continued through the holidays. We did take Christmas off. So what's happening at the observatory? AUI has issued some restrictions due to the Omicron pandemic. Not much will affect the user here. We'll continue operations as normal, but we will be restricting visits to Green Bank. So if you're planning to come to visit Green Bank, we'll probably have to defer that until February or later. We have changed some of our in-person meetings to virtual. Would like to point out that the Green Bank call for proposals is now been issued for next semester. These are due February 1st. And I put in the chat a link to one of the GBT proposal planning workshops. And that will be on the 20th of January from 2 to 5 p.m. Eastern, and another on January 26th from 9 to 10 a.m. Eastern. There's a link to the registration. It will be fully virtual this year due to the COVID situation. So think about your proposals, get them in. We did have that special call for low frequency, large programs. Those proposals are being evaluated. We hope to get disposition letters out early next week. So if you put in a proposal for that, you will hear from us shortly. So again, Happy New Year, everybody. We're very excited about today's talk, and I'll pass it over to Jay to introduce our speaker.
Thanks, Jim. Yeah, today's speaker is Jorge Pineda from JPL, and he'll be talking about characterizing the ionized and neutral phases of the ISM with far infrared, fine structure, and radio recombination lines. And just let me remind everyone, you submit questions through the Q&A box in the lower right of your screen. And this webinar is being recorded and will be available for viewing within a few days. Take it away, Jorge.
All right, so thank you very much. Let me start to share the screen now. And all this goes like this. Can you see it?
Yes.
Wonderful. Okay, so thank you very much for the invitation to give this talk. And so I'm Jorge Pineda from the Propulsion Laboratory. Today I'm going to tell you about using far infrared spectral lines as tools for characterizing the ionized and neutral phases of interstellar medium, which is basically the focus of the work we are doing here at JPL. But of course, there's a very strong connection with radio observations in the radio continuum and radio recombination lines. So I will tell you a little bit more about that. So our main kind of goal is to understand the regulation of star formation in galaxies. Ionized gas regions are powered by and shaped by the radiative feedback of newly formed massive stars. And the stellar feedback is thought to be the main mechanism regulating the star formation in Milky Way-like galaxies, which in turn is a key driver of galaxy evolution. So characterizing the energetics and structure of ionized gas regions and their relationship with the neutral phases of the interstellar medium is important for understanding the role of the stellar feedback and the regulation of star formation in galaxies. So if we look at the kind of the full picture of the interstellar medium, we have different phases going from warm ionized medium cold and neutral atomic hydrogen phases, and dense molecular clouds, H2 regions, diffuse molecular clouds, and almost all these phases are traced by fine infrared fine structure lines. For example, C+ is really tracing ionized gas, atomic gas, the skins of molecular clouds, while lines like nitrogen 205 and 122 micron trace ionized gas regions. Even if you look at the very close vicinity of stellar clusters, you can trace them with lines like 0388 microns or 53 microns or N357 microns. And of course, at the same time, all these H2 regions are traced by radio continuum observations, also recombination lines. So there's a nice synergy within far infrared and radio astronomy when we are looking at characterizing the properties of interstellar medium. So for the far infrared, we used to, of course, we have Herschel, which is a very nice telescope, and we got a lot of very interesting data here. Now we have Sophia flying, and we are getting a lot of very good data. But for the future, we are going to have, hopefully, fly this year, I think, with Gusto, that will map C+ and M+ and O1 lines in the galactic plane. And a year later, we are going to have Astros, which I'm the PI of this project. I'll tell you a little bit more about that, which it will be focused on mapping a nice nitrogen lines. So everything more or less started with Herschel, because we did the GOT-C+ survey, which was a volume-weighted sample of about 500 nanoscience in the disk of the Milky Way. So we sampled in ionized carbon with the HiFi instrument at high spectral resolution. So we sampled in the galactic plane every 1 degree in the inner galaxy and every 2 degrees in the other galaxy. And the goal was to sample as many clouds as possible over a very wide range of physical conditions, so to allow us to have a statistical information about the clouds on the Milky Way. And we were able to convert, because we have the velocity resolution, we could separate different clouds along the line of sight. We were able to make a map like this, so velocity versus galactic longitude for the galactic plane. And these lines here are projections of different spiral arms, models of different spiral arms in this map. And you see that ionized carbon here is shown, is tracing mostly spiral arms in our Milky Way. And we got a lot of very nice results with this. In terms of luminosity, for example, we found that about 40% of the C+ luminosity is coming from star-forming regions, kind of PDRs, 20% coming from atomic clouds, diffuse atomic gas, ionized gas, contribute about 22% of the C+ emission in the Milky Way, but also we found a significant fraction of diffuse molecular clouds that we call the CO darkish 2 gas that we are kind of starting now to characterize with C+ observations and other tracers. But we actually did another follow-up of this survey in ionized nitrogen. And that was done with the PAX instrument, so it's velocity unresolved. And this was Paul Korsberg was the PI of this. But we sampled the same line of size of GOT-C+ in the two nitrogen lines at 205 and 222 micron with the PAX instrument, so 140 line of sights. And we also observed 10 line of sights in the M+ 205 micron velocity resolve. So why we are interested in the nitrogen lines is because, well, as the ionization potential of nitrogen is 14.5 eV, so it's all nitrogen is ionized only in regions where hydrogen is fully ionized, and the far infrared structure lines of ionized nitrogen are excellent tracers of density structure and dynamics of the H2 regions. It has two transitions, 205 and 122. These are the energy levels. And what is nice about this is that the ratio of these two lines is a very nice measure of the electron density of the gas within a reasonable range of densities, and it's not very sensitive to temperature. So it can be a very nice tool to characterize electron densities of gas. And we did that work in the galactic plane. And what was kind of surprising for us is that the ratio of these lines are fairly uniform across the galactic longitude. So almost everywhere in the galaxy, we have a relatively similar ratio that translates in a density range between 10 and 50 particles per cubic centimeter. So that means that there's a widespread component in the Milky Way where the density doesn't vary very much, but it's actually a lot higher to what we expect from the warm ionized medium, which is 0.1 particles per cubic centimeter, but also are not the densities that we expect from ultra-compact H2 regions, right? So what is the origin of this, and what is what are the characteristics of this ionized component of the interstellar medium? And well, with the velocity and resolve observation from PACS, it's very hard to tell. So we need to resolve the line of sight to separate clouds along the line of sight, right? But the problem is that at Sophia altitudes, the frequency of the 122 micron line of nitrogen is highly absorbed by the wings of an atmospheric line. So with Sophia, we are not able to do this line at high spectral resolution. We can go to a balloon, and I'm going to tell you a little bit more about that. But for the moment, there's very little access to this. So there's a way to go around that to characterize the density of ionized gas without that line. And this is using radio recombination lines. So RRLs are spectrally resolved and obscure traces of ionized gas, and they provide an ambiguous determination of the emission measure. And that does allow us to study the electron density distribution. And hydrogen recombination lines, of course, are the brightest, but you can also see helium recombination lines in highly ionized regions. And also you can see also carbon recombination lines kind of in the skins of the molecular clouds. So the line to continuum ratio, of course, gives you the electron temperature. And they also can trace the Lyman continuum photons, so they can trace the star formation rate. So recently, I mean, GBT have been pioneering this, is that broad instantaneous bandwidth receivers, right, can allow us to observe many recombination lines simultaneously, and we can stack them together. And that brings the sensitivity and the signal to noise ratio we can go much deeper in radio recombination lines, and we are starting to see a very nice results because of that. So we decided to do a same survey that we did in COTC Plus in radio recombination lines. So for the northern part, in collaboration with Lauren Anderson, we used the Green Bank telescope to map the recombination lines in the northern sky. And for the southern sky, we are using the DSS 43 70-meter telescope that we have in Australia as part of the Deep Space Network, both in X-band. So the resolution for the DSS 43 is 110 arcseconds and 80 arcseconds for GBT at X-band. So I'm going to show you some results of this survey. For 10 line of sight, we observe at velocity resolve in the M+ 205 micron line. But I'm also preparing a kind of a more broader work paper on all these line of sights. So these are the 10 line of sight we observe in M+ and recombination lines and C+. So in black, you see C+, in green is the M+, and in red is the recombination lines. So there's in general a nice correspondence between the nitrogen and the recombination lines, what you expect. The ratios from C+ to RRL and M+ to RRL vary very much from place to place. So there's obviously a wide range of physical conditions going on in this line of sights. So this is how the longitude velocity map of the Milky Way looked in C+, and this is how it looked like in recombination lines. So there's some, I haven't told you that before. So there are some correspondence, but there's of course both coming from the spiral arms, but you see a little bit difference in the distribution of these two tracers, and you see also some high velocity clouds here, and which are also interesting for the dynamics of the galactic center in the recombination lines. So you can use the M+ to RRL ratio actually to derive the electron density loop, because the M+ 205 micron intensity is proportional to the fractional population of the GP1 level, which is plotted here, which depends on the electron density and the column density of M+, right? While the RRL is proportional to the electron density times the column density of H+. So the ratio give us this quantity here that actually is also dependent on the electron density. So you can actually use this ratio to derive the electron density in these clouds. In this case, velocity resolved. And that's what we did. This is an example of in one line of sight. So what I'm showing you here is, so in gray is the recombination line, and in the color coded is what you will expect. I mean, given the density of the nitrogen line and an electron density, what you will expect to see in recombination line, right? So there are many. So in this case, you have two components, and the density at this component at plus 50 kilometers per second, the densities are relatively high, maybe 50 particles per cubic centimeter. But in this other component, the densities are lower, maybe 10. So you can see difference along the line of sight in the density structure of these clouds. So we did it for all these 10 line of sights that I mentioned before, and we found a range of densities between 6 and 170 particles per cubic centimeter. And these are basically very consistent with what we saw with M plus 205 and 122 micron from Herschel packs by Paul Goslet. So, and again, these are a lot higher than what you expect from one ionized medium, and also lower than what you expect for ultra compact H2 regions. About the environment, and I think it's important to understand what is going on with this kind of diffuse, widespread ionized gas component, is that if you plot the position we observe and compare them with all these H2 regions that were cataloged by Lauren Anderson, most of our line of Gotzi plus line of sights go far, kind of doesn't fall in the center of these classical H2 regions. They're kind of in their outskirts, right? So that means that again, so this is kind of support the idea that there's a widespread component of ionized gas that is away from the compact H2 regions. So that means that the ionized gas is actually very extended in the galactic plane. Another bonus, let's say, that you can do with this work is that, so as I told you, you can derive the electron density with the M plus 2 RRL, but if you have the density from the two lines, the 122 and 205 micron, you can in principle also derive the ratio of the nitrogen to H, N plus to H plus, and that gives you an idea of basically the metallicity of the gas, the nitrogen abundance as a function of galactocentric distance. And in general, most of what we know about this is coming from optical observations, but because of the dust absorption, we only know about the solar neighborhood and older galaxies. So in this case, we actually can go all the way to the galactic center. So we can have a new measure of the nitrogen abundance close to the center of the galaxy. And in this case, I mean, the blue line here is what the gradient that people find in with the optical observations, and it's actually pretty similar to what we see in the inner galaxy. So it seems that the nitrogen abundance increases as we approach the galactic center. So, this work was made based on single positions in the galactic plane, but of course it will be actually to really understand the impact of stellar feedback and into the regulation of star formation, we need to be able to start mapping star forming regions. So we need to characterize them and compare them with the stellar components and other traces, right? So because the velocity information and this observation can determine the three-dimensional structure and kinematic of H2 regions and understand the role of stellar feedback. So motivated by that, we proposed some time ago the Astros mission, which is a balloon-borne far-infrared observatory that is scheduled to fly in December 2023 from Antarctica at an altitude of 40 kilometers for 21 days, which is equivalent of about 500 hours of observing time. So it has a 2.5 meter telescope, which is large for far-infrared, of course, small for radio. And that's enable high dynamical range, high spectral resolution observations of galactic and extragalactic star forming regions. Astro will have two 4-pixel heterodyne arrays covering the 1.4 to 1.5 and 2.5 to 2.7 terahertz spectral range, enable simultaneous observation of fine structure lines of ionized nitrogen, 205 and 122, and other key spectral lines. Astro will fly a 4K low power cryocooler that doesn't require liquid helium, so it enables lifetime long missions. So we are going to observe the 3 star-forming regions, the 336 region, the 305 region, and the Carina Nebula. 336 and 305 are relatively earlier stage of evolution before the action of supernova explosions, while the Carina is clearly being affected by supernova. So by comparing the ionized gas distribution of these 3 regions, we will determine the relative effect of different stellar feedback mechanisms in the terrestrial medium. We are also going to take advantage of the 2.5-meter telescope that enable observation of extragalactic sources, and we are going to map the entire disk of the galaxy M83, shown here, in this M+122 and 205 micron, and we are going to, with this, study the distribution of ionized densities and the star formation rates in this galaxy and compare it with what we know about the spiral density waves and the stellar bar in this galaxy. So we have been doing some preparation work. This is something that has been done with in the DSS-43 antenna in Australia. So we recently installed a broadband spectrometer there, and this you can find more information about this in this reference. It operates at K-band, and we can observe simultaneously the 17 to 26 gigahertz bands. So these are 8 IFs with 2 polarizations, so we can really start to do stacking and get deeper into these clocks. And this is what we are doing for the Carina Nebula. So in this case, the observations are about 40 arc seconds, and here I'm showing you the radio continuum emission map there, and you can see the kind of the clusters at the center and all these structures here. And then we also see them very similar structures in the recombination line, but it's not only this. We have the velocity information, and if you do the velocity maps of this, you'll start to see this evidence of a large-scale outflow going on out of Carina in the ionized gas, and I think that will be a very interesting way to quantify and characterize the role of stellar feedback. So this will be really a very important data set for when Astros comes, and all 3 components, we will learn a lot more about what is going on with feedback in the Carina Nebula. So just to finish, so far infrared spectral lines provide an obscure view of ionized and neutral phases of the terrestrial medium. RRL and M+ are powerful tools that can be used to characterize electron density distribution of H2 regions, and therefore be used to characterize the impact of stellar feedback in the terrestrial medium of galaxies. And current and future FRI facilities will enable detailed characterization of ionized gas components of the ISM that will allow us to understand the role of stellar feedback in the regulation of star formation in galaxies. Thank you.
Thanks very much for a fascinating presentation. Let me remind our audience to submit questions via the Q&A box in the lower right, and we have one already. There's an apologies from a first-year master's student, but who wants to know how ionized nitrogen line observations give information on the dynamics of the H2 region, and how do the ratios give information on the densities, electron column densities.
Yeah, so let me show this again. So about the dynamics, of course, we are doing high spectral resolution observations, right? So with sub-kilometer per second, kilometer per second is, and clouds along the line of sight have different Doppler shifts, right? And if this thing, for example, is expanding, so expanding bubble, for example, you should be able to see different components along the line of sight that tells you that the gas is moving, and you can make some estimate about the mass and the velocity of the clouds to estimate the energy that is injected into the ISM. About the densities, let me go to this one. Yeah, so I mean it's or maybe that one is better. This one. So the level population of these lines, the M+205, for example, depends on the density of the gas, right? Because of collisions, right? And so there's a dependence of the level population of energy level on the density of the gas. So for the 122 line, you have a different dependence, right? And if you plot the ratio of them, they will give you a kind of a nice function of the electron density that can be related to the ratio that you observe, and that can give you the electron density.
We have another question. Do you plan to observe M33?
M33 is southern sky or northern sky?
Northern sky.
Yeah, okay. We are flying from Antarctica, so that's we are not able to see M33 with
Okay. Okay.
Yeah.
Now, I had a question about the nitrogen abundance gradient across the galaxy, which is, it seems like it's an order of magnitude.
Yeah. And actually, I've been doing some extra work on that, and I've been trying to observe also N3 lines at 57 micron, especially in the galactic center, because it could be that the gas in the galactic center is actually highly ionized, and not all the nitrogen is ionized there. And I've been finding that it's actually could be even higher here. So then the nitrogen abundance can go even higher in the center of the galaxy, and that could be related with the. So nitrogen is formed in kind of massive stars and also in intermediate mass stars. So it could be that there's a lot of kind of a little bit older stars in the galactic center, and they are kind of producing more nitrogen than, or for example, oxygen or other things.
I think you just may have answered the next question, which is it possible that nitrogen is only partially ionized?
Yes. I mean, of course, we have the recombination lines, and the helium lines are next to it. So I've been trying to look of our line of sight whether there's anything obvious where you can see nitrogen helium lines next to the hydrogen line. I will tell you that the radiation fields are strong enough that nitrogen is not ionized. So it's double ionized or triple ionized, right? It's not obvious, but I've been also using SOFIA to observe the N3 lines, and I've been having some detections, especially in the galactic center. So I've been trying to account for that. And so far, I mean, it's work in progress, let's say. In Carina, if in the Carina Nebula, we're going to observe with Astros, I have evidence that in the very close to the clusters, there's a lot of helium lines, so the gas is highly ionized. So then we are not, then in that position, we are not accounting for all the nitrogen with N+. We will need N3 observations.
There's another question that you mentioned that the ionized gas detections are usually associated with the outskirts of H2 regions. Are there examples where you see ionized gas that is not correlated with star-forming regions?
No, I haven't seen that. They are correlated because they're close, right? But we're not looking at the center of a star-forming region, right, in the galactic plane. But away from that, I think we are all seeing basically the effect of a star formation over a larger scale in the galactic plane.
Mm-hmm. Another question about how sensitive your observations are, or your determinations to the different angular resolutions from the far IR to the radio.
All right, so I obsessed on that too. I did some experiments for the galactic plane, and using the kind of the gas continuum emission from hot dust continuum, and smooth the data to different resolutions and see whether you see a difference. And you don't see much. It's there, but it's not a major effect.
Okay, yeah. We have a question about LMC observations. Are any of those planned?
Oh, the LMC, I love the LMC. Yeah, so I have some recombination line observations in the LMC. With Astros, we may be able to see the LMC. The problem is that we will have to use batteries to go to the LMC because of the position of the solar panels. But I'm considering maybe trying to do some observations with 30 grados. The Gusto balloon, right, will map the LMC in, let me show you if I find it, a picture of it. We'll map the LMC in C+, hopefully. Here, this balloon. One of the baseline plan is to map the LMC in ionized carbon, and maybe nitrogen and oxygen, but I think it will be mostly sensitive to ionized carbon.
Okay, thank you. I don't see any more remaining questions. So let me thank you once again for your presentation and remind everyone who's listening that it will be available on our website in a few days. And please join us 2 weeks from now on January 19th, when Emily Moravec will be presenting a talk on exploring merging galaxy clusters and radio galaxies at a redshift of order 1. We look forward to seeing you then, and thank you.
Okay. Ole. Hi, Ole.